Welcome everybody to today's rendition of the point distribution webinar. Thanks for coming today. Today we have as a speaker Fátima Lizarte from the Universidad de Cantabria, speaking about a sequence of well-conditioned polynomials. After the talk, there will be time for questions, and then after that, there will be time for tea, socialization. So please feel free to stay on to hang out a bit. But Fátima, if you will.
Thank you. First of all, I would like to thank the organizers for giving me the opportunity to talk in this webinar. I am going to talk about my first work with my supervisor, Carlos Beltrán. We have studied the following problem. Find explicitly a sequence of univariate polynomials Pn of degree n with condition number bounding about by n. It is posed by Michael Suff and Stephen Smail in 1993. By find explicitly, they meant giving a handy description or describing an algorithm running in polynomial time and where the exact real arithmetic is available to solve the problem. Our goal is to give a simple and direct answer to Suff and Smail problem. The results obtained can be seen in this reference. From now on, we will denote the problem, our problem, or similar expression to Suff and Smail problem, to this problem. The talk is organized as follows. First, we explain the definition of the condition number of polynomials. Secondly, we state the origin of our problem, its relation to other interesting mathematical problems, and previous knowledge until this work. Next, we give the main result and comments on its proof. Finally, we show the most important references used in this work. So, the first question is, what is the condition number of polynomials? The condition number of polynomials is a quantity associated with the series of a polynomial that encodes how sensitive these series are to perturbation of its coefficients. We have the following situation. We have the space of inputs and space of outputs. Polynomials lie in the input space and series lie in the output space. The latter one can be C complete numbers. We consider this set formed by the pair input and output of this input. In this case, the input is a polynomial and the output is a root of this polynomial. This set is a Riemannian manifold called the solution variety. Let f be a polynomial as set a root of f. The pair f set lie in the solution variety. Now we want to observe in this direction, how the root set changes under a small perturbation of the coefficients of the polynomial f. If the root set suffers a small perturbation, then the polynomial f is well conditioned in the root set. Otherwise, it is ill conditioned. So, considering the natural projection, the condition number of the polynomial f in the root set can be defined in this way, because we want to measure in this direction how the root set changes under a small perturbation of f. If there is not mentioned a concrete root, then we take the worst case, that is, we take the maximum of the condition number of the polynomial f between all its roots. If the root set is a diverse root, then by definition, its condition number is infinitive. Now we are going to talk about the origin of our problem. It is posed by Michael Suff and Stephen Smail in 1993. Michael Suff is an American mathematician who has done research into dynamical system and complexity theory. Stephen Smail is an American mathematician too, now for his research in dynamical system, topology, theories of computation, and mathematical economics. Also, he was awarded the Fields Medal. Two curiosities. On the one hand, Michael Sub and his wife collect art from around the world. You can see their collection in this website. On the other hand, Stephen Smale has one of the finest private mineral collections in existence. Some photos of his collection can be found here. At the end of the 20th century, the president of the International Mathematical Union wrote a number of mathematicians with suggestions that they describe some great problems to be solved in the next century. Among these mathematicians was Smale. He compiled a list of 18 problems in mathematics to be solved in the 21st century, known as Smale's problems. He chose them with this criteria: simple statement, personal acquaintance with the problem, a belief that the question, its solution, partial results, or even attempts at its solution are likely to have great importance for mathematics and its development in the 21st century. Currently, only 3 problems of Smale's list has been fully solved. The statement of Smale's list can be seen in this reference. Our problem has its origin in what is known as Smale's 17th problems, which is about the share for an efficient algorithm running in polynomial time to compute series of systems of polynomial equations. In 1981, Suf and Smale began working together on complexity theory of solving systems of polynomial equations. In general, there is a not general formula to solve this type of system, but there exists a method called homotopy method, based on solving a system from another whose solution is known. The idea is to modify the known system little by little, observing how its solution changes until we reach the system we want to solve. The idea is not difficult to implement computationally. In fact, Suf and Smale proved that this method can be done in a totally rigorous way once the initial part has been correctly selected. So they started looking for the right initial part. They thought that a good candidate for an initial part could be made up of well-conditioned polynomials. It's here that our problem is posed. Soon, they realized that explicitly describe such a sequence of well-conditioned polynomials was a difficult task, and they began to study. In short, the motivation to Suf and Smale to pose the problem was the share a good starting polynomial to be used in homotopy method for polynomial root finding and therefore solving system of polynomial equations. Finally, Smale's 17th problem was solved in this temporary order by Carlos Beltrán and Luis Miguel Pardo gave a probabilistic algorithm with polynomial time complexity. Bagiser and Cooker found a deterministic algorithm with quasi-polynomial time complexity. Lauret found a deterministic algorithm with polynomial time complexity. So, Smale's 17th problem was finally solved without finding the solution to our problem. Now, we are going to give the most important previous knowledge until this work. Suf and Smale proved that given a random polynomial of degree n of this 4, as the sum of monomial with coefficients are obtained from the standard complete Gaussian distribution with these 2 parameters, then it has condition number at mod n, with probability at least 1/2. This result does not alone give an algorithm to generate well-conditioned polynomials, but it is a way of guaranteeing that our problem must have solution because there are many well-conditioned polynomials of all degrees. In fact, Sufan-Smale relaxes the problem, changes the condition at month n to as month nc. We see a constant. However, the problem remains difficult. On the other hand, our problem is related to potential theory. Before giving the next previous knowledge, it is necessary to define the logarithmic energy of spherical points. So let me define the logarithmic energy of a collection of n points on the sphere as the sum of logarithm of the inverse of their mutual distances. And let us denote by this the minimum possible value of the logarithmic energy between all collection of n spherical points. So and Smale proved that if n spherical points such that their logarithmic energy is very close to the minimal logarithmic energy in this way are known, we see a constant, then one can construct a solution to relax problem of Sufan-Smale. How? Well, first, keep in mind that the stereographic projection is a map that allows to uniquely identify point on the sphere to point in the complete plane. So, the solution, just taking the polynomial whose zeros are obtained from the stereographic projection of the n known spherical point, whose condition number is at most this quantity. However, finding collection of spherical points satisfying this condition is an even more difficult problem than ours. Despite by this result, Sufan-Smale posed the problem of finding collection of spherical points with a small logarithmic energy. In this sense, this was later included in Smale's famous list of problems for the 21st century. Hence, this fact is the reason for the exact form of the problem posed by Sufan-Smale that is nowadays known as Smale's seventh problem. So, Smale's seventh problem is to give a simple and efficient description, or alternatively, describing an algorithm to place n point on the sphere such that the logarithmic energy is very close to the mean. Although it is a simple statement problem, it has proven to be a problem of great theoretical difficulty. In fact, this value is not fully known. The current knowledge about the minimal logarithmic energy on the sphere is this asymptotic expression, where kappa is the continuous energy on the sphere, defined like that. This sigma is the normalized uniform measure, and C log is a constant with this bound. In fact, the upper bound has been conjectured to be an equality. In addition, there are some conjectures about the number of critical points of the logarithmic energy on the sphere. Some researchers conjecture that the number of local minimum grows exponentially on n, but no precise result is known. Distributing point in a sphere or other set is a very classical problem. Its modern formulation in terms of energy minimizing configuration is due to the discovery of electron, Thomson, in 1904. He proposed a certain atomic model that today we know that it is 4. Thomson held that atoms are uniform spheres of positively charged matter in which electrons that are negatively charged particles are embedded, popularly known the plum pudding model. Thomson posed the following question: in which position would n electrons lie to other minimize the electrostatic potential? On the other hand, there are many samples in natura of well-distributed points in a sphere or other set. And a sample in natura of well-distributed points in a sphere can be found in pollen grains. The next 4 pictures correspond to the distribution of pores in pollen particles. These pictures and other more can be found in this book. The solution to Smail's seventh problem is only known in a very simple and concrete cases. For this value of m, the solution is given by the vertices of regular polygon in the equator and the poles. More precisely, for n2, 3, 4, 5, and 6, the solution is given by this configuration, respectively. In fact, for n7, numerical experience suggests that the solution could be given by this configuration, but a rigorous proof is not known. Well, our problem has been recently solved by Carlos Bertrán, Ujué Tallo, Jordi Marzo, and Joaquín Ortega Cerdá in a peculiar way, not lately, by a closed formula for large and unknown m, and by a shared algorithm for the rest of the cases. The solution can be found in this reference. The closed formula is an enormous formula, and the idea of the shared algorithm is the next one. We do an enumerate of rational zeros and generate polynomials with them. Since computing the condition number of a polynomial given its zeros is immediately, if such polynomial has condition number at most its degree, then it is valid, and otherwise it is rejected. So these two items produce a polynomial time algorithm for the problem. For this problem is solved. In addition, they prove that the optimum value of the condition number of a polynomial of degree n is a term of this form. In fact, the condition number of their closed formula is upper bounded by a term of this form, but they didn't get the constant hint here. The problem was solved in a few months before starting my thesis. Carlos Bertrán posed me to continue the study to the Suff and Smail problem because it would be great to find a simple and direct answer. So our aim is to give a simple and direct answer to Suff and Smail problem with an upper bound completely explicit for the condition number of such a sequence. Have we achieved this goal? Well, we have described a simple formula for a sequence of well-conditioned polynomials of degree n, given of this form, 4n squared with n a positive integer. So we have achieved our goal when n is given of this form. In this case, our f polynomial is given by this expression, where the terms rj, hj are defined like that. The function rho can be seen here. Its condition number is upper bounded by this explicit expression. The first three polynomials of our sequence correspond to the degrees 4, 16, 36, respectively, can be found in this table. So the question now is, why this polynomial? Where does the constructing polynomial of degree n come from? Note that these polynomials are defined by its zeros, and they can be seen under a stereographic projection to a set of spherical points constructed. Before defining our set of spherical points, we recall in this slide the definition of the stereographic projection. So, this is a map projection obtained by projecting points on the surface of a sphere from the North Pole to point in the plane tangent to the South Pole. Then, for any point P on the sphere except the North Pole, there exists a unique line through the North Pole and P, and this line intersects in the plane in exactly one point. Analytically, with this notation, we use this formula for projecting point to the sphere to point in the complete plane. And in a positive case, we use the other one. So thanks to the stereographic projection, each point on the sphere corresponds uniquely to a point in the complete plane. Next, we construct a set of spherical points which are, under the stereographic projection, the series of the well-conditioned polynomials of our sequence. So the total number of points is n given of this form. With the note like that, our set of spherical points. These points are equidistributed in parallels which are symmetric with respect to the equator. How many parallels? The equator is the F parallel. So we have n-1 parallels above the equator, and by symmetry, we have n-1 parallel below the equator. So the total number of parallels is 2n-1. Which is the height of each parallel? Hj is the height of the jth parallel and is defined like that. The height of the equator is 0. And the analytical definition of a parallel can be found here. So we know the number of parallels, its height. So we have fully indeterminate the parallels. Now we place point on each parallel. How many points? Rj is the number of points by parallel. So the parallel of the height Hj contains Rj equal 4j points, which are a set of Rj roots of the unit defined by the parallel. More precisely, they are given by this explicit expression. The values of Hj are chosen in such a way there is a bound with normalized area Rj over M, whose central height is Hj. Here we can find the analytical definition, a graphical description can be seen in the graphic. Finally, by symmetry, it is satisfying these two equalities. Here we show a graphical description of our set of spherical points for different values of M. So for N3, we have 36 points with this configuration. The other example is for N7 and N20. So the question now is, how can we prove that the constructing polynomial of degree M is well conditioned? Since a polynomial is a two-multiplicating constant defined by its series and they can be seen as spherical points, one can aim to give a formula for the condition number of a polynomial that depends uniquely on the associated spherical points. Suv and Smain accomplished this task. So the condition number of a polynomial P of this form can be computed from this formula. Here we have a constant that depends on the degree of the polynomial P. And here we have a maximum in I of this quotient that depends uniquely on the hat set, which are the associated spherical point to the series of the polynomial P. So from our set of spherical points, we get an upper bound for this formula. In this way, under this condition, we obtain these two results. The first one is an upper bound for the numerator, and the second bound is an upper bound for the denominator. To prove these two results, we have done an in-depth study where we have used a wide variety of analytical tools. In fact, it is necessary quite previous result to come to them. What happens when n is smaller than 5? In this case, our proof is computer assisted thanks to this expression that's allowed to compute exactly the condition number of a polynomial for simple cases. This norm is the Bombieri-Weyl norm defined like that. It is similar to the Euclidean norm, but its coefficient has this weight. Other question. Why do we take this set of spherical points? In general, our set of spherical points can be considered a particular case of a set called the Hammond ensemble, proposed by Carlos Beltrán and Ujué et al. They were looking for the collection of spherical points with a small logarithmic energy, and they found this set. The Diamond ensemble has two fundamental properties. It is made up of well-distributing and well-separating points. This is essential to get a small upper bound for this formula. For the numerator, we need well-distributing points, and for the denominator, we need well-separated points. In addition, one can think that modify our set of spherical points slightly, our proof can be very likely adapted for general M. However, this touch is still out of reach because the explicit computation becomes too complicated. To M, I write one note in my tablet with 4 main steps to prove our main result. Each step corresponds to a section of our paper, but I write only a general idea. And I have only a camera, so you can see my face when I write. Sorry for this. Okay, I start. Once we have defined our set of points, in order to prove our main result, we proceed as follows. Step A. Given any point Q in the sphere, any bound B in the sphere, we consider the central parallel BQ of B. We compare these two integrals. where sigma b is the normalized area of the band, defined like that. These two integrals, we have two integrals with the same function. In the first integral, p belongs to the band, and in the second one, p belongs to the central parallel Q of the band. We conclude this, that is, this integral is approximately equal to the normalized area of the band times the expected value of the same function in the central parallel. Note that this result is independent of the construction of our spherical point set. Step B. Comparison between minus kappa n and this sum. Well, I denote this integral like that. And this other, so. And here we comparison between this term and this sum. Recall that kappa is the continuous energy on the sphere. So minus kappa is this integral. Now, we divide the integral in the different bounds associated to our point set. So we have this. Now, using this notation, this sum can be right of this form. For any Q belong to the sphere. Now, from step A, it is satisfied this. The normalized area of our band is Rj over M. Then it is satisfied this. We have this from here, and now we use this relation from A. And we denote this sum as Sm. The difference between these two terms turn out be rated small as said if Q is too close to the poles. We prove that where the symbol hides essentially the term this with Q belong to the band BL. Step C. We then compare the value of this term with that of the sum where the PJK are the RJ points in the corresponding parallel. Both quantities are again very similar except for the parallel, which is the one close to Q. From this, we get the following bound. Pi is our points, so this term can be right of this form. And we prove this. This is Sn. So from B, it is satisfy this. This essentially gives an upper bound for the numerator. In the formula of condition number of polynomials. Once the details are set. Finally, step D, the same kind of argument using also that our point set is well separating, produce a lower bound for the denominator. Value for all fish I. This almost finish the proof of our main result. All the appearance of this symbol are estimated with concrete constant. So this fourth step is the general idea to prove our main result. Only general idea. It is necessary many details. So finally, we can see the most important references used in this work. This is all. Thank you very much for your attention.
All right. Do we have any questions for the speaker? I had at least one question. So from what I was understanding from this talk, so in order to get a good conditioning number, would any set of points with a small logarithmic energy on the sphere work?
Only but the sound is very much because I am with the table.
Okay.
Can you write in the chat?
Mm-hmm.
Well, the diamond sum has two fundamental properties. It is made up of well-distributing and well-separating points. So this is very important to get a small upper bound for this formula, because for the numerator, we need well-distributing points. For the denominator, we need well-separating points. We prove we have proven other set to extend our main result for general M. But we need define a function of a number of points for different case, depend of the parallel. So this is very difficult because the explicit computation become too complicated. Maybe other set could be work, why not? But we use this set. This is the reason for the well separating and well distributing points. Maybe, but I'm not sure because there are many previous results to count these two main bounds. So maybe, but I don't know. Depend.
Okay. Okay. Other questions for the speaker? All right, well then, if not, I will stop the recording.